Welcome to Chemistry 101 Chemistry Review. Basically, these are the last quizzes, your replacement quizzes, Quiz 11 and Quiz 12. And I didn't feel like we had appropriate enough time in class to go over the answers and how the answers were derived. So I'm going to take this moment to make this video, and hopefully you can go back through your quizzes and understand how each answer was produced. Okay, the first problem, what is the energy of a photon with a wavelength of 97.8 nanometers? So the first thing you're going to have to do is use the formula E equals h nu, and nu is the frequency. And since you're given wavelength, which is lambda, you're going to have to use C equals lambda nu. You're going to need to solve for nu and then replace this equation in terms of lambda. So in order to isolate nu, you have to divide both sides by the wavelength. That cancels that out. And then you can rewrite it C equals lambda equals nu, and then you put this in for nu, so it's E equals hc over lambda. Now, the nice thing is you have two constants there that are given to you on the periodic table. You don't have to memorize them. One is Planck's constant, 6.626 times 10 to the negative 34 joules times second. And then C is 3.00 times 10 to the 8th meters per second, and then you divide by lambda. Now lambda is given to you in nanometers, and if you notice you have meters in your constant, so you're going to have to convert that to meters. You learned how to do this in chapter 1, 97.8 nanometers. There are 1 and 9 zeros in nanometers for every 1 meter. And so if you get your calculator out and you do that, 97.8 divided by 1, that gives you, let's do this in scientific notation, 9.78 times 10 to the negative 8th meters. And so if you put that in for there, you can go ahead and do 6.626. And you need to practice this because calculators sometimes can be tricky when you're first learning how to do exponents. Okay, when we put this in the calculator, you should get E equals 2.03 times 10 to the negative 18. The meters cancel out, seconds cancel out, and you get joules, which is a unit for energy. And if you look at your problem, that is answer B. Okay, what is the mass percent of chromium? When you look at this needs to be subscripts. So this didn't copy over very well, but it's Na2Cr4O7. And when you're doing mass percentage, so the first thing you want to do is calculate the formula of mass. So you have 2 sodiums, you have 4 chromium, and you have 7 oxygens. So this is 2 times, if you look at the periodic table, and you see the mass of sodium is 23. Grams per mole. sodium. Chromium is 52 grams per mole, and oxygen is 16 grams per mole. So this is 46. This is 208. This is 112. When you sum all this together, you add them all together, you get the formula mass of 366. So this asks for chromium, so you want the part of chromium over the whole. So basically you're doing 208 divided by 366 times 100%. And that works out to be 56.8%, which is C. Okay, once again, this copied over without the subscripts on these, so you can make that correction. For glucose, it's C6H12O6, formula weight 180.156. Okay, you need a combustion reaction. So let's just go ahead and write that combustion reaction. So C6H12O6 plus oxygen goes to CO2 plus water. And in that combustion reaction, you have to balance it. So the quickest way to see is that you have 6 carbons, and all your carbons need to be here. So there's 6 carbons on the product side. And then you can go to your hydrogens. You got 12 hydrogens, so if you put a 6 here, 6 times 2 is 12 hydrogens, and then figure out how many oxygens you have. So that's 6 times 2 is 12 oxygens plus 6 oxygens, so that's 18 oxygens. You have 6 oxygens here, and so if you put a 6 here, that's 12 oxygens, so that gives you 18. So now it's balanced. So the first thing you have to do is have a balanced equation because it's asking for grams of glucose, and you're starting with the amount of oxygen. So if they're giving you the amount of oxygens, 12.45 grams of oxygens, and it's asking for grams of glucose, you're going to have to do the mole-to-mole bridge. So you want to go from grams of oxygen to mole of oxygen to mole of glucose to grams of glucose. Now, in order to do this, of course, you have to use the molar mass. And to go from mole to mole of one substance to the other, you need to use the coefficients in your balanced equation. And then to go from mole to gram, you're going to use molar mass again. So now that's your plan. And now you do your plan. So to do your plan, you need to start with your given, which is here, 12.45 grams of oxygen. And the nice thing, it tells you that there's 32.0 grams of oxygen in 1 mole of oxygen. And you look at your coefficients and you see that for 6 moles of oxygen, you have 1 mole of glucose because you see the coefficients. And then for 1 mole of glucose, you have the molar mass, which they tell you is 180.156 grams. And so when you take this and you take this number and divide by 32 and then divide by 6 and then multiply by 180, you should get 11.68 grams, which is answer B. Okay, the next one, how many grams of sodium chloride must be used to prepare 76.4 milliliters of 0.466 molar solution of sodium chloride? I do believe this is probably, as a whole, the class's weakest area. And there are a lot of questions asked dealing with concentrations on this exam, so I would really focus my energy on this. Whenever you see this molar concentration, like I've said in class, just go ahead and break it into a conversion factor. So this equals 0.466 mole of sodium chloride. And since we're dealing with milliliters, just go ahead and put that over 1,000 milliliters. That's your conversion factor. And then you can start with a given. And remember, a given is not a conversion factor. A given is a number with a unit by itself. So you can say 76.4 milliliters of sodium chloride solution. And then you want the milliliters on bottom. So here's your conversion factor. So 1,000 milliliters, 4.6 or 0.466 mole. Now we have mole of sodium chloride. So where we're at here, because this cancels out, we are at mole of sodium chloride. So in your plan, you can go from milliliters of sodium chloride to moles of sodium chloride by using molarity. Notice I didn't make this a cursive M, it's not molar mass. What is it asking? Then go back to the question. What is the question asking? How many grams of sodium chloride? Well, you guys know how to go from moles of sodium chloride to grams of sodium chloride. You just do molar mass. And what I'm going to do is make that a cursive M. You get that from the periodic table. Or in this case, it's given to you right here. So for 1 mole of sodium chloride, you have 58.44 grams. Now look at this. Milliliters cancel out, moles cancel out, and you're left with grams of sodium chloride. How many grams of sodium chloride? So it's that simple. Then you do 76.4 times 0.466 divided by 1,000 times 58.44. And that equals 2.08 grams. And when I look at this, I find the answer right here is D. Once again, you're going to have to see this big M, this big concentration, and you're going to have to make it in terms of a conversion factor so you can do dimensional analysis if you want the correct answer. Okay, once again, this question is dealing with, you see the big M, you're dealing with concentration. So go ahead and for the first one, before you do anything, you just go 0.570 mole of magnesium. You got to be able to write this. Magnesium hydroxide. Magnesium's a 2+, hydroxide's an OH minus. So you have to have 2 of them. So, and then that equals, and what are we dealing with? We're dealing with milliliters. So I'm going to go ahead, instead of writing 1 liter, I'm going to say 1,000 milliliters. And then here we have 0.260 mole of sodium hydroxide. So that's just a 1+. So that's how you do that formula. Sodium hydroxide equals 1,000 milliliters. So these are my conversion factors. Now, I'm given 2 givens here. I'm given a number with a unit and a number with a unit by itself. So now we'll read the question and try to figure out what is it asking. So if it's saying 100 milliliters of magnesium hydroxide solution with this concentration, well, guess what? If I have 100 milliliters of magnesium hydroxide solution using molarity, big M, I can get moles of magnesium hydroxide. Okay, and right here, I'm given 250 milliliters of sodium hydroxide I use this conversion factor, milliliters, 1,000 milliliters equals 0.260 mole of sodium hydroxide. These milliliters are going to cancel out. I have moles of sodium hydroxide. That's important because we can work with moles. So we have the number of moles of magnesium hydroxide and the number of moles of sodium hydroxide. What is the final hydroxide concentration? So this is your plan. You got to go from milliliters of hydroxide, magnesium hydroxide, got to do these individually, to moles of magnesium hydroxide, and then moles of OH. And then you do the same thing, milliliters of sodium hydroxide to mole of sodium hydroxide to mole of OH. Now look at this. So how do you go from milliliters to moles? You use the molarity. How do you go from moles of magnesium hydroxide to moles of hydroxide? Well, for 2 moles, you got 2 moles of hydroxide for every 1 mole of magnesium hydroxide because of the 2. Same thing here. Milliliters of sodium hydroxide, use molarity, and then for every mole of sodium hydroxide, you have 1 mole of hydroxide. Right, so now you just do the numbers, do the math. So 0.570 mole of magnesium hydroxide. No, you want to start with volume. Sorry about that. So erase that. Let's start with the volume. You're given 100 milliliter of magnesium hydroxide. And now your conversion factor, 1,000 milliliter, you have 0.570 mole of magnesium hydroxide. And for 1 mole of magnesium hydroxide, you have 2 moles of hydroxide. And when you do that math, you should have 100 times 0.570 divided by 1,000 times 2. So this works out to be 0.114 mole of OH minus contributed from the magnesium hydroxide. Now you have 250 milliliters of sodium hydroxide, 1,000 milliliters, 0.260 moles. Using the concentration gives you moles of sodium hydroxide. And for 1 mole of sodium hydroxide, you have 1 mole of OH minus. And the reason why is because that subscript is actually a 1. So 250 times 0.260 divided by 1,000 is 0.065 mole of OH minus. Now you add these two together, okay? So you add 0.114 mole of OH minus from the magnesium hydroxide plus 0.00065 mole from the sodium hydroxide. And you're going to divide this over the total volume, which was 100 milliliters plus 250 milliliters. So that gives you 0.00051 mole over 1 milliliter. But to get it into molarity, you've got to convert it to mole per 1 liter. So now you just take the 0.00051 mole over 1 milliliter, and then you say for 1,000 milliliters, you have 1 liter. And so you take that number, multiply it by 1,000, and you get 0.51 molarity. And that answer is answer C. Okay, so in this problem here, nitrogen gas is liberated in the following reaction. Now I've noticed people are getting really confused on these. So let's look at the equation. So it's your gas laws. I'm going to rewrite this because the subscripts did not carry over. I think that can get confusing. Nitrogen gas is liberated. Well, you got solid, solid gas. Actually, this should be a reaction arrow. Okay, so this is your only gas. So they're showing you the equation where gas is liberated. What volume, we want to know the volume, and it's going to be in liters, is generated at 23 degrees Celsius. So go ahead and put your temperature, 23. Now we're dealing with gas laws, so you're going to have to go ahead and convert that to Kelvin. So that will be 300 Kelvin. 1 atmosphere, so go ahead and define 1 atmosphere for pressure. Now you're given an amount. You're given 2.76 grams of sodium azide over here. So you're going to have to use stoichiometry where you go 2.76 grams of sodium azide. What's the plan? You're going to go from grams of sodium azide, which is a solid, and you're going to have to go to moles of sodium azide because you cannot go from grams to moles of a different substance. And this, since we're at moles of sodium azide, then we can go to moles of nitrogen. When you're doing PV equals nRT, you cannot do that on a solid. You must do it on a gas. So N is of the gas. So you got to come down here and get moles of N2, which is your gas. A lot of people try to just convert this to moles and then put it in, but you're not going to be able to use find a volume of sodium azide solid in the ideal gas law. Okay, so then you solve the PV equals nRT in terms of volume. So V equals nRT over P. You isolate your variable. So that's your plan. So your plan is to find moles of nitrogen, 1, and then to solve for volume equals nRT over P. So let's do that. 2.76 grams of sodium azide, and then you're giving your formula weight here. So for 65.02 grams of sodium azide, you have 1 mole of sodium azide. And then look at your balanced equation for your coefficients or your ratios. For 2 moles of sodium azide, you have produced 3 moles of nitrogen gas. All right, so now let's put that in our calculator to get in. 2.76 divided by 65.02 equals times 3 divided by 2 gives me 0.06367 moles of N2. Now I can put that in for N. So let's go. Solve for volume equals 0.06367 mole of N2 now. R 0.08206 liters atmosphere mole Kelvin. And then temperature is 300 K. And your pressure is 1 atmosphere. And the units should cancel. Moles, moles, atmosphere. Atmosphere, Kelvin, Kelvin. And I get volume equals 1.57 liters. And the difference in the number might be just my rounding. So go ahead and choose A. Okay, which of the following orbitals have the highest energy for neon? Well, looking at neon, you just need to get in the practice of writing, whenever you get these kind of questions, go ahead and write the electron configuration. That's usually how you problem solve for these. So neon, I found it on the periodic table, and I see it's 1s2, 2s2, 2p6. Okay, these higher N shells, so your N number, these are your N numbers. This is the principal quantum number. It's the distance your valence electrons, or just your electrons in general, are from the nucleus. So if you increase your N number, it's further, the electron is further from the nucleus, and therefore it has higher energy. So the orbitals then, and you also have the energy slides. So a p orbital, yeah, that's right. A p orbital will have a higher energy than an s orbital. Okay, so you have your highest would be these last ones that you write, and that would be B. What shape? You do need to know the shape. So we've talked about, this is kind of messed up here. This is A, B, C, D, E. So this is a principal N number of 3, so N equals 3. And then your L number, which is your shape, equals 2. Okay, you got to memorize. L equals, if it's 0, then it's a sphere. And that is an L number of 0. It looks like this. If L equals 1, it's a dumbbell shape. Looks like this. And there's 3 of them. There's 3 orientations. So the M sub L number here would be 0. This is a -1, 0, +1. Remember, you have N quantum numbers that tell the address or distinct definition of defining that electron, M sub L and then M sub S. And this is your spin. It's either +½ or a -½ because it's either clockwise or it's counterclockwise. When you have an electron, we denote that by spinning up or spinning down. The M sub L is the orientation. So for S, you're going to have 1 orbital. For a P, you're going to have 3 orbitals. For a D, you can have 5. These are odd. You have to kind of memorize this. F, you can have 7 orbitals. And we do the orbitals with the boxes. And then you get them in. So this is L equals 0. This would be L equals 1. This would be L equals 2. And this would be L equals 3. And then your M sub L numbers here, since there's only 1 orientation, would be 0. Here would be -1, 0, +1. Here would be -1 or -2, -1, 0, +1, +2. Here would be, I didn't draw enough orbitals, did I? We need 7. So this would be -3, -2, -1, 0, +1, +2, +3. So what shape describes the 3D? The D is an L equals 2. You memorize that. And that is more of a donut shape. So the answer is E. What is the electron configuration of chlorine atom? So you could just, so chlorine shorthand would be, you find chlorine, you go to the noble gas before it, and so that's neon, and then you go to 1, 2, 3, the third row, and it's 3s2, 3p5. If you do that longhand with all the electrons, 1s2, 2s2, 2p6, 3s2, 3p5. You need to check it to make sure. The number of electrons for a ground state chlorine would be 17 for neutral. 17 electrons, so then you count these superscripts, and 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. So you're good there. And then you find these should be all superscripts. You can't have a P8. No. So it's not in there, so this would be the answer. You have to write that in. Okay, how many electrons can have n equals 3? How many electrons can have n equals 3 and L equals 2 at the same time for a given atom? So you're looking at 3, and what's L? L, so L equals 0 is S, L equals 1 is P, L equals 2 is D, and you have 5 orbitals. So we're talking about a 3D, so you're talking about every quantum number can have a 3, 2. Okay, so how many orbitals are there for D? There's 5 orbitals. And you have an M sub L number, -2, -1, 0, +1, +2. So each electron would fill up these orbitals as Hund's rule, 5 across, and then going down, that's 10 electrons. These are your transition metals. So basically your valence electrons are going to be located in these d orbitals. So the answer is D. Okay, which ion has a manganese of +6 oxidation state? So these should all be subscripts. Didn't copy over. To find out what your metal is here, you look at your non-metal. And remember, these have to sum to 0 because there's no charge except for this one. This sums to +2. So that's a magnesium oxidation state of +2. This one, O2, is -2 times 2. So that's a -4. And since there's only one magnesium, that's a +4. This one here, 3 times -2 is a -6. And there's only one magnesium, so that's a +6. So C is your answer. Okay, what is the electron configuration for bromide? Now notice that this is, if you look up bromine, and you see that bromine is number 35, so that's your proton. And since a neutral bromine would have the same number of electrons as protons, so it would have 35 electrons, but this is a bromide ion, so it has one more electron than proton, so this is going to have 36 electrons. So we have to do an electron configuration for 36. So you fill them all up. You can go to the noble gas before bromide, so that's argon, and then you count 1, 2, 3, 4. Bromide is in the 4th, so 4s2, and then you have your transition metals. I'm looking at the periodic table, 3d10, and then 4p5. So you got to look at the periodic table, and you got to find the bromide. Now that is for your ground state bromide. I always do ground state first. Well, then you add an electron. So you're going to add the electron in the highest energy state. So this one would be argon, 4s2, 3d10, 4p6. Now all our answers are given us not the shorthand, so I'm going to go ahead and fill in what argon is. 1s2, 2s2, 2p6, 3s2, 3p6. And I'm going to look for all of these, and the answer should be A. Okay, once again, we're dealing with molarity, concentrations, and I think this is our weak area here. So pay particular attention and work extra problems. When we see this, so sodium hydroxide, we're going to go ahead and make that a conversion factor. So that's 0.500 mole of sodium hydroxide equals, since we're dealing with milliliters, I'm just going to go ahead and say 1,000 milliliters. And then we have sulfuric acid, H2SO4. Now that's 1.50 molar, so that's mole, 1.50 mole of sulfuric acid equals 1,000 milliliters. Now, when you're given a volume, so here you have 17.5 milliliters of, 17.5 milliliters of 1.50 molarity of H2SO4, that is essentially telling you the moles of H2SO4, because we can just basically use 17.5 milliliters H2SO4 solution, and for 1,000 milliliters we have 1.50 mole of H2SO4. So that's the power of the concentration. So let's go ahead and get us our moles of sulfuric acid. 17.5 times 1.5 divided by 1,000. So that gives us 0.02625 mole of H2SO4. So now, what is the volume of the sodium hydroxide that's needed to react with 0.02625 moles of sulfuric acid? Well, you're going to have to write a neutralization reaction, because we are going to go from mole of sulfuric acid to mole of sodium hydroxide, and then we're going to go to the volume of sodium hydroxide. And so to go from mole to mole, we need coefficients in a balanced equation to change that substance. And then when we get to sodium hydroxide, to go from mole to volume, we have to use the conversion factor right here. So let's write our balanced equation. In a neutralization reaction, you have to be able to recognize you have a strong base, because you memorize those, and you memorize your strong acids, H2SO4, and they are going to make the salt, sodium sulfate. You need to know sulfate is a 2- and sodium is a +1, so you're going to need 2 sodiums with 1 sulfate, and then you're going to make water, because you make some kind of ionic compound, a ± salt and water. Now you want to balance it. So if you have 2 sodiums over here, then you need 2 sodiums here. And now we have 1 sulfate and 2 sodiums. How many hydrogens do we have? 1, 2, 3, 4. So we're going to need 2 here. Okay, so now we have our coefficients. You can check that. And we can go from our moles of sulfuric acid, 0.02625 mole of H2SO4 over 1. And then look at our coefficients, for 1 mole of H2SO4, we have 2 moles of sodium hydroxide. And then we look at our conversions. For 0.500 mole of sodium hydroxide, we have 1,000 milliliters, because we have that concentration. So now we can take that and do the math. Multiply the top, divide the bottom, and we get 105 milliliters. That is not an option here, so just go ahead and fill in option F is 105 milliliters. Okay, a sample of nitrogen gas occupies 25.0 liters, 37 degrees. So we got temperature and pressure. What is the volume at STP? Well, I've told you, every time you see this STP, go ahead and write a new conversion factor. 22.4. Okay, so like I said, when you see this STP, go ahead and use the conversion factor that you have to memorize, that a mole of gas equals 22.4 liters for 1 mole. Okay, so remember that's like the size of a basketball. Now, what's interesting, that's my basketball, by the way. See, basketball. You're given these other conditions, and then it asks for the volume. So what you want to do, since you have moles here, you want to use the volume of 25.0 liters, the temperature, 37.0 degrees Celsius. You got to have that in Kelvin to use the gas law, PV equals nRT. So that ends up being, I think, 310 Kelvin. And you have a pressure of 550 millimeters of mercury. And you do have to have this memorized. It's 760 millimeters of mercury for this test is 1 atmosphere. And when you do that, you will get, let's just go ahead and do it. 550 divided by 760, that's 0.724 atmospheres. That's your pressure, your temperature, your volume. Now you have R equals 0.08206 liters atmosphere mole Kelvin. And you have to solve for moles. So now you do PV equals nRT, and you solve for N. So you got to isolate N. So N equals PV divided by RT, and then you plug and chug. So you put 0.724 atmospheres times the volume, which is 25.0 liters, divided by R, 0.08206 liters atmosphere mole Kelvin, times your temperature, 310 Kelvin, and then let's go ahead and solve that. 0.724 times 25 divided by 310. That is moles of 0.7115 mole. And then you use your conversion factor here. So it's just 0.7115 mole of gas. For 1 mole of gas, you have 22.4 liters. So you take that by 22.4 liters, and you get 15.9 liters. And that is answer A. Okay, this one, calculate the specific heat. So you know that you're going to have to use this equation here, Q of a metal. Okay, so you're going to have to use Q of metal equals the mass of the metal times the specific heat of the metal times your change of temperature, which is T of the final minus T of the initial. And then Q of the metal equals negative Q of the water. So the heat is going from the metal to the water. You might actually have the negative sign the other way, but basically you're going to set these two equal to each other. Mass of the metal times specific heat of the metal times delta T equals the negative times the mass of your water times the specific heat of your water times the delta T of the water. And this one's the metal. So I would just go ahead and calculate your delta T for your metal is initially at 246, and then the final is the same temperature. So 35.6 degrees Celsius minus 246 degrees Celsius And that works out to be negative 210.4 degrees Celsius. And then do the delta T for your water, which is 35.6 degrees Celsius minus 20 degrees Celsius, and that works out to be 15.6 degrees Celsius. Now you have all your variables, you can put them in. So let's just do metal in red, and we'll do water in blue. So the mass of the metal is 4, oh, we're already messing up, aren't we? Okay, the mass of the metal is 4.56 grams times, we don't know the specific heat of the metal. Okay, that's what we're going to look for, times our delta T, negative 210.4 degrees Celsius. And then we do the other side, the water equals the mass of the water. Let's go ahead and put our negative sign out here. 10 grams times the specific heat of the water, which is given to us, 4.184 joules, grams, degrees Celsius, times the delta T of the water, 15.6 degrees Celsius. Now, when you get your calculator out and you multiply 4.56 times negative 210.4 degrees, you're going to get C, specific heat of the metal, times negative 959.424 degrees Celsius times grams. And then this is going to equal, you should get a negative 652.704 joules. And then you want to solve for the CS, the metal. This is connected by multiplication, so you're going to have to divide both sides by negative 959.424 degrees Celsius. Divide both sides by this number. And then the negatives cancel out to give you CS of the metal equals 0.680 joules, grams, degrees Celsius. And if you look at that answer, it is not up there, so that is answer F. There you go. Okay, this. How many neutrons and protons does... Okay, so review how, in your book, how electrons, or how the mass of elements are reported. So here you have... Okay, so if you remember correctly, you have your element, and then you have A and Z. And A is the mass number, and Z is your atomic number. And if you remember, your atomic number is also the number of protons. And then usually here you have your charge. So this could be a charge. So if there's no charge there, then it's neutral. And if it's neutral, then the number of electrons equal the number of protons. And you can find your atomic number by looking at where it falls in the periodic table. So for scandium at C, if you find scandium on the periodic table, you see its element number 21. So that means it has 21 protons. And since there's no charge here, then that means it also has 21 electrons. And this number here is your A number, and it's your mass number. And your mass is your protons plus your neutrons to make up the nucleus. And here it's 45, so your mass is 45 and your protons are 21. So if you solve for your neutrons, you see that you have 24 neutrons. And your answer then would be 21 protons and 24 neutrons. Okay, the last question we have is a limiting reagent problem. And you can recognize this as a limiting reagent because it gives you the moles of butane, C4H8, and also gives you the moles of oxygen. And this is a combustion reaction. So you're taking butane and you're reacting it with oxygen to give you CO2 plus water. And you have to be able, anytime you get a reaction like this, you're going to have to write the combustion reaction to balance the equation because you need those coefficients. Because it's giving you the amounts of butane, the amounts of oxygen, and it's asking how much CO2 is produced. And so the only way you can go from an amount of butane to CO2 is the mole-to-mole bridge, or the amount of oxygen to CO2 is mole-to-mole bridge. You have to have these coefficients. So the quick way to do this is to see that there's 4 carbons in butane. So you need to put a 4 in front of your carbon dioxide. And then you look at your hydrogens. You got 8 hydrogens. Well, this is your hydrogen over here on the product side. What multiple can you multiply by 2 to give you 8? 4. Okay, there's your 8. Now we're going to have to make sure our oxygen is balanced. So we have 4 times 2. We have 8 oxygens plus 4 oxygens. So on the product side, we have 12 oxygens. Over here, we have 2 oxygens. What can we multiply by 2 to give us 12? Okay, 6. Okay, now we have a balanced equation. Now we have to go from moles of, so this is our plan. We're going to go from moles of butane to moles of carbon dioxide. And we're going to go from moles of oxygen to moles of carbon dioxide. And then, so that's the first thing we do. Well, first thing we do is we balance our equation. The second thing we do is we figure out how many moles of carbon dioxide. And then we're going to choose the limiting reagent, which is the least number of moles of CO2 produced. And that's going to be our answer. Okay, so let's just go ahead and do that. We have 4.5 mole of C4H8, and for 1 mole of C4H8, we have 4 moles of CO2. Okay, and if we do the math on that, we should get 18 moles of CO2. Now we have 15.3 moles of O2, and for 6 moles of O2, we have 4 moles of CO2. And when you do the math on that, you get 10.2 moles of CO2. So your limiting reagent is the least number, because 10.2 is less than 18, and this is oxygen. And so then the answer here would be C.